and I expected something more like a factor of 7. And so, in d over L, where I expect a factor of 7, I only see a factor of 2. So I said to myself, oh my goodness, why didn't I ask them for an elephant? The real clincher would be the elephant, because if that goes way off scale, maybe we can still rescue the statement by Galileo Galilei. And so I went back, and they said, okay, we'll give you the femur of an elephant. They also gave me one of a moose, believe it or not. I think they wanted to get rid of me by that time, to be frank with you. And here is the femur of an elephant. And I measured it, the length and the thickness. And it is very heavy. It weighs a ton. I plotted it. I was full of expectation. I couldn't sleep all night. And there's the elephant. There is no evidence whatsoever that d over L is really larger for the elephant than for the mouth. These vertical bars indicate my uncertainty in measurements of thickness, and the horizontal scale, which is a logarithmic scale, the uncertainty of the length measurements is in the thickness of the red pen, so there's no need for me to indicate that any further. And here you have your measurements, in case you want to check them. And look again at the mouth and look at the elephant. The mouth has indeed only 1 centimeter length of the femur, and the elephant is indeed 100 times longer. So the first scaling argument that S is proportional to L, that is certainly what you expect, because an elephant is about 100 times larger in size. But when you go to d over L, you see it's all over. The d over L for the mouth is really not all that different from the elephant, and you would have expected that number to be with the square root of 100, so you expect it to be 10 times larger instead of about the same. I now want to discuss with you what we call in physics dimensional analysis. I want to ask myself the question, if I drop an apple from a certain height and I change that height, what will happen with the time for the apple to fall? Well, I drop the apple from at height h, and I want to know what happens with the time when it falls. And I change h. So I said to myself, well, the time that it takes must be proportional to the height to some power alpha. Completely reasonable. If I make the height larger, we all know that it takes longer for the apple to fall. But that's a safe thing. I said to myself, well, if the apple has a mass m, it probably is also proportional to the mass of that apple to the power beta. I said to myself, gee, yeah, if something is more massive, it will probably take less time. So maybe m to some power beta. I don't know alpha, I don't know beta. And then I said, yeah, there is also something like gravity. There is the Earth's gravitational pull, the gravitational acceleration of the Earth. So let's introduce that too, and let's assume that that time is also proportional to the gravitational acceleration. This is an acceleration. We'll learn a lot more about that, to the power gamma. Having said this, we can now do what's called in physics a dimensional analysis. On the left, we have a time. And if we have on the left side a time, on the right side, we must also have time. You cannot have coconuts on one side and oranges on the other. You cannot have seconds on one side and meters per second on the other. So the dimensions left and right have to be the same. What is the dimension here? That is t to the power 1. It's that t. That must be the same as length to the power alpha times mass to the power beta times acceleration. Remember, it is still there on the blackboard, has dimension L divided by time squared, and the whole thing to the power gamma. So I have a gamma here, I have a gamma there. This side must have the same dimension as that side. That is non-negotiable in physics. Okay, there we go. There is no m here, there is only one m here, so beta must be 0. there is here L to the power alpha, L to the power gamma. There is no L here, so L must disappear. So alpha plus gamma must be 0. There is t to the power 1 here, and there is here t to the power minus 2 gamma. It's minus because it's downstairs. So 1 must be equal to minus 2 gamma. That means gamma must be minus 1/2. But if gamma is minus 1/2, then alpha equals plus 1/2. End of my dimensional analysis. I therefore conclude that the time that it takes for an object to fall equals some constant, which I do not know. But that constant has no dimension. I don't know what it is, times the square root of h divided by g. Beta is 0, there is no mass. H to the power 1/2, you see that here, and g to the power minus 1/2. This is proportional to the square root of h, because g is a given and c is a given, even though I don't know c. I make no pretense that I can predict how long it will take for the apple to fall. All I'm saying is I can compare two different heights. I can drop an apple from 8 meters and another one from 2 meters, and the one from 8 meters will take 2 times longer than the one from 2 meters. The square root of 8 to 2, 4 over 2 will take 2 times longer, right? If I drop one from 8 meters and I drop another one from 2 meters, then the difference in time will be the square root of the ratio that will be twice as long. And that I want to bring to a test today. We have a setup here. We have an apple there at a height of 3 meters. We know that the length to an accuracy, the height of about 3 millimeters, no better. And here we have a setup whereby the apple is about 1.5 meters above the ground, and we know that to about also an accuracy of no better than about 3 millimeters. So let's set this up. I have here something that's going to be a prediction of the time that it takes for one apple to fall divided by the time that it takes for the other apple to fall. H1 is 3 meters, but I claim there is an uncertainty of about 3 millimeters. Can't do any better. And H2 equals 1.5 meters, again with an uncertainty of about 3 millimeters. So the ratio H1 over H2 is 2.000, and now I have to come up with an uncertainty, which physicists sometimes call an error in their measurements, but it's really an uncertainty. And the way you find the uncertainty is that you add the 3 here, and you subtract the 3 here, and you get the largest value possible. You can never get a larger value. And you'll find that you get 2.006. And so I would say the uncertainty is then 0.06. This is a dimensionless number because it's length divided by length. And so the time t1 divided by t2 would be the square root of h1 divided by h2. That is the dimensional analysis argument that we have there. And we find, if we take the square root of this number, we find 1.414 plus or minus 0.0, and I think that is a 2. That is correct. So here is a firm prediction. This is a prediction. And now we're going to make an observation. So we're going to measure T1, and there's going to be a number, and then we're going to measure T2, and there's going to be a number. I have done this experiment 10 times, and the numbers always reproduce within about 1 millisecond. So I could just adopt an uncertainty of 1 millisecond. I want to be a little bit on the safe side. Occasionally, it differs by 2 milliseconds. So let us be conservative, and let's assume that I can measure this to an accuracy of about 2 milliseconds. That is pretty safe. So now we can measure these times.